The aim of today, my aim of today, is to get us back on schedule, because it's annoying for you to have to prepare 2 sets of slides. It's even more annoying for me to have to prepare 2 different lectures. Last week I talked about efficiency and optimality, and I talked about externality and pigou taxes. And what I should have done was also talk to you about public goods. So that is what I'm going to do, and then we're going to turn to cost-benefit analysis and target setting more generally. So, what is a public good? You must have seen this before. A public good is a good that is non-excludable and non-rivalrous. And in contrast, a private good, and you're much more familiar with that, is both rivalrous and excludable. So the example that you see here of a private good is an ice cream, because I used to eat this in summer, a bit inappropriate now. But an ice cream is a good example of a private good. It is rivalrous because if I eat the ice cream, you cannot. Because I have eaten it and therefore the ice cream is gone. It's physically no longer there. And that is how rivalry is best understood as a physical concept. An ice cream is also excludable because in the period between me buying the ice cream and me eating it, that's typically a fairly short period, but in that short period you may not eat the ice cream because it's legally mine, and you eating it would be theft. And that's morally and legally wrong. So excludability is a legal concept, and rivalry is a physical concept. And that is how I think these two can be best told apart. The classic example of a public good is a lighthouse. If you're a sailor, you're on the sea and it's night, you can see the lighthouse and you know where is the coast and you have a rough idea where is the port. But the fact that you see the lighthouse does not prevent the sailor in the ship next to you from also seeing the light. Right? So there's no rivalry in consumption. We can all watch the light. That's why we put it high up on a tower so that people can see it from every angle. It's also non-excludable in the legal sense. It is not that some sailors are allowed to look at the lighthouse and others are not. And you could think of that there would be such a rule, but there isn't such a rule, right? So that is a public good. So the difference between public and private goods happen in 2 dimensions, one a physical dimension and the other a legal dimension. And that then immediately implies that there's also 2 mixed goods that are typically referred to as impure public goods, although I think that is a bit, doesn't help a whole lot to call them that way. The first of these 2 impure public goods are open access, resources, or common goods. And the classic example is sheep grazing on the commons of a village. It used to be that every village in England and across the world had a commons, and everybody who lived in that village legally would be allowed to graze their sheep or their cows or their pigs on the commons. And as long as you lived in the village, You could not be excluded from this. So you had a legal right to put your sheep on the commons. Right? So it's non-excludable. But of course, the sheep are not there just to stand around. The sheep are there to eat the grass. And if my sheep eat the grass, your sheep cannot eat the same grass. Right? So there is a physical interaction between the animals. That is, there is rivalry in consumption. That is what we call an open access or a commons, open access resource or a commons good. We also have the opposite, goods that are excludable but non-rivalrous, and they are known as club goods. Or they actually come under various names, and club goods actually also mean different things to different people, but let's call them club goods. And the example that you see here is indeed of a club. So you need to pay an entrance fee to go into the place where the concert is held, right? And if you don't have an entrance ticket, you are not allowed in. So it is excludable, right? There's a fence around it, and unless you pay, you won't get in. So it is legally excludable. But as soon as you're in, I can listen to the music, and you can listen to the music, and that doesn't affect either of us, as long as you don't dance too wildly. It doesn't matter, right? So there is no rivalry in consumption of the services that the band is providing, but there is excludability in the access, right? So that is another example. There's one example of a club good. Now the problem with public goods is that they're underprovided, because you cannot exclude people from enjoying the services of the public good. You cannot charge for them, so you cannot charge them, so there's no reason to provide the right amount of the public goods, right? And that then immediately also spills over to the commons goods, right? There's no reason to provide for the commons, because you cannot charge the people to put their sheep on there. The non-rivalry means that there's overconsumption. I get this wrong. The non-excludability means that there's overconsumption, right? The problem with the commons is that you cannot exclude people from putting their sheep on. So everybody has an incentive to put as many sheep on as possible, because the extra grass that they eat, that comes at a cost, but that cost is spread over all the users of the commons. So you have a reason to overconsume. And if you cannot charge, there's a reason to underprovide, right? So that is the basic problem with public goods. This slide says the exact same thing. We can put a little bit more structure on this. And that is the question, what is the right social provision of the public goods? And it was Samuelson, Paul, when he was much younger than he looks here. Samuelson is still alive. I'm pretty sure he's still alive. It's just quite amazing. He made his breakthrough in the 1940s as a very young man. And he gave us most of the microeconomics that you know is due to this guy here. He also works on public goods. And one of the things that he showed that the efficiency condition, allocative efficiency that we talked about last week, product mix efficiency, that the marginal rate of substitution should be equal to the marginal rate of transformation. That is a condition that holds for private goods and for private goods only. For public goods, the marginal rate of transformation, that is the production side of things, should not equal the marginal rate of substitution, but rather the sum of the marginal rate of substitution. Or private goods should be vertically aggregated and public goods should be horizontally, and there should be a T in there, horizontally aggregated. It sounds abstract, and it is abstract, and it is in a sense arbitrary, and mathematicians would disagree with economists here. Somebody may have told you that everybody puts the x on the x-axis and the y on the y-axis, except for economists who put the y on the x-axis and the x on the y-axis. This goes back to a Congress in Paris in 1888. So economists graphically have cause and effect the wrong way around according to everybody else, right? And that then of course also means that we got verticality and horizontality wrong. But what do I mean by vertical and horizontal aggregation? So at the top left for you guys, you're looking at the two demand curves of two people. This is from the Kolstad book. So Anna is a proper name, Anna, and then the guy has an American name, Brewster. Americans have very strange names. And these are their private demand curves, right? And both slope downwards. That is, if the price is low, they want a lot, and if the price is high, they want little. So that is what is going on there. Then the graph that is next to it is a graph you are used to. This is how we aggregate, how we go from individual demand functions to a social or an aggregate demand function. In this case, there's only two people in the market, so that is fairly straightforward. So if the price is, so if there's very little on the market, right, then Brewster is prepared to pay 5, and Anna is prepared to pay only 2.5. So the first good goes to Brewster, right? And that continues and continues and continues, that Brewster essentially dominates the market. But then when the quantity hits, I think it's slightly over 5, maybe it's 6 even, Anna actually kicks in, because from that point on, Anna is actually prepared to pay more for the good because Brewster's demand is partially satisfied, right? And that then continues because Anna's curve is shallower than Brewster's curve. If you look at who wins, it's actually Anna's demand that dominates. And this we call horizontal aggregation, right? Because essentially the aggregate demand curve is the sum of the private demand curves if you look at it horizontally, right? Now, in a public good, the demand for, if this good were public, would be this aggregate demand curve rather than that one. And essentially, if there's very little on the market, then Brewster is prepared to pay 5, and Anna is prepared to pay 2.5, but there's no rivalry in consumption. So Brewster can have his public goods, and Anna can have her public good, but we don't need to choose between the two. Right? So one is prepared to pay 5, the other is prepared to pay 2.5. So the total demand is 7.5. Right? Right? In the private good, the total demand is actually, or the total willingness to pay, is 5. Because if there's nothing on the market, Brewster will pay 5, Anna will pay 2.5, and the good goes to Brewster, and Anna doesn't matter, right? So that's the difference that rivalry makes. We add up the two demand curves horizontally, no, vertically. And the result is this demand curve for the public good and that demand curve for the private good. And here we see the two demand curves together. This is the rival good, this is the non-rival good. Then we have a hypothetical supply curve as well, a marginal cost curve. And we have two equilibrium points, one for the rival good and one for the non-rival good, right? So that is what Samuelson means with the sum of the marginal rate of substitutions should equal the marginal rate of transformation. And I've swapped vertical and horizontal. The math is right, the text I am not sure of at the moment. Okay, now Lindahl has a follow-up on that. He says, well, for public goods, the optimum is where the sum of the marginal rates of substitutions, which is the sum of the willingness to pay, or the sum of the prices that each of us are willing to pay for the public good, that should equal the supply price. And in the Lindahl equilibrium, we all have our personal prices for the public good. We all have our personal contributions to the public good. And that should equal the margin it's supply. This is a nice theoretical concept. It's a logical consequence of the Samuelson condition that I showed before. But it is, of course, completely impractical in any way that we would measure everybody's individual willingness to pay for something and then add it up, and that is how we supply public goods. But that is what we should do theoretically. There's a few more things I can say about the provision of public goods. So I'm going to consider a very boring economy. We have an economy where everybody is the same. It's very simple. And we consume two things. We have a private consumption and of just one good, and we have a public good, right? And our utility depends on our income W and on the total provision of the public goods G. Simple as that. The small g is how much we individually contribute to the public good. There's no government or anything in this economy. It's the voluntary provision of a public good. So if we spend little g of our income W, that means that we have W minus G left for consumption of the private good, right? And that goes into our utility function. The G bar that you see is the sum total of the contributions to the public good of all the others in the economy. So the total provision is small g plus G bar is G, right? This is just a change in notation. And then because everybody is identical, G bar is n minus 1 times G, where n is the number of people in the economy, right? This graph has two axes. On the horizontal axis, we put little g, our contribution to the public good. And on the vertical axis, we put the contributions of all others to the public good, G bar. And then this curve here is an indifference curve. This is where utility is constant. And what we would like to provide is, I mean, the public good means something to us, right? So we would be inclined to provide something towards the public good. So the utility function, or the indifference curve, sorry, has to come down first and then go up later. And then the one that we would provide of ourselves is somewhere here. It's obviously smaller than our total income. It's somewhere there. So consider, for instance, a road, right? Then, yeah, it would be awkward to not have any paving at all. So at the very least, we would sort of like keep the road in front of our own house in reasonably good condition. We would not be willing to pay towards roads far away from where we are and where we work or where we go to school, but we would be willing to pay something to make our own life a little bit more comfortable, right? So that particular part of the public good that directly contributes to our welfare, yes, we are prepared to make an effort there. So that is why, even if it is a public good, we would still be willing to pay something towards it, right? Purely hypothetical, right? So this is one indifference curve. Now, what happens if the others provide more? Well, for the same level of provision that we do, there is more public good. So if the others provide more, we become happier, right? So that's one thing. The higher indifference curves, or the indifference, utility 1 is greater than utility 0, and utility 2 is greater than utility 1, right? That I think is trivial. Also, the more of the public good that is provided by others, the less we need to do, right? And the more of our income we can keep to buying a private good. So the minimum of these indifference curves should shift for you guys leftwards, right? And that implies that the best response curve is this. So this is how much we would provide of the public goods as a function of what the others provide of the public good, right? So that is our best response. So now introduce a supply curve. Well, if it were a private, if we leave it to this, this is essentially our demand for the public good. If this is the supply of the public good, then supply meets demand at this point here, right? This is the private, the optimal private permission, the individually rational private provision of the public good, right? Gn for us, G bar n for the others. But this is not optimal. Optimal is where your supply equals your marginal utility. And that is, in the next graph, that is this point here, where the slope of this curve is equal to the slope of our indifference curve, our utility function, right? So that is the social optimum. The marginal cost of supplying the public good equals marginal utility of the public good. And this is the individually rational provision of the public good, right? So this basic theory predicts that public goods, if left to the private market, will be undersupplied, right? It also means, because here we are on utility curve 1 and here we are on utility curve 2, it also means that we are less happy, right? It's not just that less of the public good is provided, but it actually reduces welfare, right? So, public goods are underprovided and overconsumed. Not just in theory. Here we have an example, a pretty neat example, from fishing on the high seas. So the way fishing rights are given is that inside the exclusive economic zone of a country, that is 200 nautical miles from the shore, roughly, the fish that swims there is owned by the country. In this case, the country is Argentina. So the fish that swim here are the exclusive property of the Argentinian government, who can then manage and control the behavior of Argentinian fishers or Argentine fishers, right? Fish that swim in the high seas, these are the Falklands, and you can sort of like see, well, there was a bit of a conflict there. Fish that swim in the high seas are not owned by anybody. So anybody can fish there, right? So the theory predicts that there's overconsumption of fish here relative to here, right? Now, what you're looking at here is transponder data. So all legal fishing boats have a transponder on the boat, and that tells you where they are and what they're doing. And this is the number of fishing hours per square kilometer. And and the lighter the color, the more there is fished. And you sort of like look at this transect here. So north of the Falklands exclusive economic zone, all the way up to the Brazilian exclusive economic zone. And the fish are to the south, right? Because they like cold, or rather they like the nutrients that come with the ocean currents that are there. And what you see, and then this is the boundary or the border of the exclusive economic zone. And what you see, that there's a whole lot of fishing activity in international waters and much less in the Argentine exclusive economic zone, right? You immediately see that. And this is not because the ocean is different there, right? This is an arbitrary line in the water and the nutrients and the temperature of the water and its salinity, and everything is the same here and here, but you see a very clear difference. Here we see the same thing, not the transponder data, which is unreliable because there's a whole lot of fishers who somehow break the transponder. Those things just keep breaking for some reason. And they come home with all this fish and nobody quite knows where they got it from, but yeah, the transponder was broken, so we don't know where they got it. So if you don't like the transponder data, you could look at night lights, and for some reason the night lights don't break, right? Because if your light breaks, then you can't see what you're doing, and they seem remarkably robust. So this is where the fishing vessels are at night, and you see the same sort of discontinuity, right? That the fishing activity is in the international waters, not in Argentine waters. You don't like spatial representations. There you see the aggregate, the distance to the boundary, fishing activity on the high seas and the EEZs of Argentina in this case, and they're the same thing, but then for the transponder data. So yes, it really does seem to be the case that public goods are over-consumed. Now I'm all tangled up in my cords. So what can you do against this, right? Well, if the problem is under provision, then the standard answer is that if the private sector will not provide, then the public sector will have to. So if we're going back to the example of the lighthouse, then all the vessels out at sea would need to come together to jointly fund the lighthouse, right? So that is one solution. But because shipping is so very international, it's actually hard to pull off. So chances are that the government will step in and use tax revenue to provide this service, right? That is what perhaps we want to do. With common goods, the issue is overconsumption. Everybody can put their sheep on the commons, so they overgraze and the soil will degrade and perhaps wash away in the next big storm. What you want to do is somehow restrict demand. And one way of doing so is to give out grazing rights and to sell grazing rights in an auction, or perhaps hand out trading rights and have them grazing rights and have them trade amongst each other. Hasn't been done for sheep. It definitely has been done for fish and other marine resources. There's a double problem here, right? It's not just that anybody can fish here. So the Vietnamese and the Chinese and the Spaniards, as well as the Argentinians. Here you have also a sort of a commons problem between people from Argentina, right? So here you can sort of like say, well, we're going to introduce a fishing quota on our own fishing fleet, right? So that would be a solution. A traditional solution to this is that the chief decides who can graze their sheep. And you appoint a regulator in that sense, or in most cases, there's a self-appointed regulator. With club goods, the problem I did not talk about that much is, we go back to the club, it is it is excludable, and then it becomes non-rival. So for the club owner, really what your best strategy, because it's a fixed cost to put up the band, right? And it's a fixed cost to put up the personnel, to serve the beer and whatever you guys drink nowadays. So the incentive for the club owner is really to let in as many people as possible, right? And then, of course, the problem in the club is that what used to be non-rival, we're all just happily dancing in a room that is big enough. If there's too many people, so of course it's in the club owner's interest, then it becomes, we essentially creating rivalry for space, right? So you want to somehow prevent that, perhaps by imposing a tax to prevent too many people from coming, or perhaps by imposing fire and fire, health and safety regulations to prevent too many people in the club, right? That would be a solution. A tax can also be used for common goods. Roads are also common goods. Nobody can tell you that you're not allowed on the road, right? So you cannot be excluded. But if you're driving someplace, then somebody else cannot drive their car in the exact same place, right? And common goods can also become congested. And there the solution would be such things as road pricing, tolls, and what have you, right? So these things can all be solved. And if they're not solved, then indeed we have a problem with underconsumption and no, we have a problem with underprovision and overconsumption. We talked about what is good and what is better. extensively. And I talked about providing public goods, and I talked about correcting externalities, but we never talked about by how much. And that is what I'm going to do in this hour. That will create a big question, and that big question we're going to talk about over the next 3 weeks. So I'm going to talk mostly about cost-benefit analysis because that is what economists do. I'm going to talk a little bit about alternatives to cost-benefit analysis, and hopefully I won't have to go too quickly through an application to the London super sewer. So this is where we are in the lecture series. We're going to talk about decision analysis, and I'm going to start by talking about efficient flow pollution. But before that, we just need to talk a little bit about trade-offs. So Robert Solow, another Nobel laureate, wrote that economists have the reputation of being unimaginative bean counters, doggedly claiming to quantify the unquantifiable and personifying Oscar Wilde's definition of a cynic as someone who knows the price of everything and the value of nothing. It is true that they, that is economists, would give a lot for a rough quantitative answer, but it only reflects the fact that any policy can be pushed harder or less hard, further or less far, and that a useful evaluation has to suggest how far and how hard. We have to advise how stringent our environmental policy should be. The beans have to be counted, if only approximately. So far, so uncontroversial, but then Solow being Solow, of course, continues with those gentle souls who merely ooh and ah over the problem or over the beans are arguably part of the problem, not part of the solution. That's a long answer. Abraham Lincoln was a little bit more succinct. The true rule in determining to embrace or reject anything is not whether it have any evil in it, but whether it have more of evil than of good. Every project, every intervention has something wrong with it, but that does not mean that we cannot do anything, because not doing anything, of course, also can do evil. Johan Cruyff has a much shorter version of this. So all three gentlemen say the same thing, right? And Cruyff said that every upside has its downside. That is, there are real trade-offs, and we have to make choices. And the choices we're going to make are about pollution, right? And as I said, pollution is an externality, an unintended and uncompensated consequence of somebody's economic actions, production or consumption, on a third party who was not involved in the decision at all. And it is important to understand the nature of the pollution that we are talking about. And that is trivially important, because if you want to solve a problem, you first need to understand the problem. But in this case, it's actually crucially important. And pollution depends on all sorts of things that happen outside of the realm of economics, mostly chemistry, biology, and physics. If we take acid rain, for instance, one of the main sources of acid rain is sulfur that is released when we burn coal to make electricity. The sulfur in the coal is actually innocent, right? As long as it's contained in the coal, it's just a contaminant there, contaminant from an energetic perspective. But it doesn't do any harm. And then we stick it in a coal-fired power plant and we oxidize it, or burn it, as most people would call it. And then that sulfur is released and becomes sulfur dioxide and gets into the atmosphere. But sulfur dioxide is perfectly harmless. And then when sulfur dioxide meets hydrogen radical, it steals the oxygen and it becomes sulfur trioxide, and it's still perfectly harmless. And it's only when it gets into contact with water that it acquires hydrogen again, and it becomes H2SO3, that is sulfuric acid. And it is at that point that it becomes damaging to health. Basically, any organism is also bad for anything that is built of limestone or calcium in any way, right? So there is these chemical transformations that are going on that actually determine whether a perfectly harmless substance turns into something that does create trouble. So that is important to understand that, right? And of course, this doesn't happen in situ. This happens in the atmosphere, in this case. And the sulfur and its various transformation is blown all over the place by the winds. So if we burn coal in Great Britain, that actually does not cause acid rain in Great Britain, because by the time the sulfur becomes sulfuric acid, it's in Poland, right? And it's important to understand that acid rain is sort of a problem that happens at a continental scale. And there's a 2-week lag between the emission, which is harmless, and the deposition that actually does do the harm. And for other environmental problems, it may not be 2 weeks, it may be 2,000 years, right? If we're talking about nuclear waste, for instance, we have a much longer time lag. And for other problems, we have a much shorter time lag and a much shorter spatial scale. So it's an important thing to understand. Now, returning to sulfur deposition, in a pristine environment, if you add a little bit of sulfuric acid, that doesn't do any harm. If you have a desert landscape, everything is destroyed, and you add sulfuric acid, it doesn't do any harm either, right? Because there's nothing left to damage. But it's in between that it does most harm, right? So it's also important to understand that your marginal contribution and the size of the marginal contribution can differ greatly depending on the natural or human-made background concentration of the things that you're talking about. Right, so it's important to understand these things and have a very detailed understanding of these things. I used to work in Ireland on water quality, and there were these wonderful chemicals that you could put in your drinking water supply, and they were absolutely great. They would kill all sorts of bacteria and take away a lot of biological contamination of your drinking water. So that is great, right? But these chemicals had the unfortunate habit of reacting with other chemicals that only occur in certain geological provinces. And yes, they would still kill all the biological contamination of your drinking water, but they would also react and create carcinogenic material in your drinking water. Now, that only happened in a small part of Ireland, in the very west and the middle. In other parts of Ireland, those natural chemicals were not in the drinking water, so you could just apply these chemicals without any bother. But in and around Galway, you should absolutely not do that. And you have to understand this to know what you're doing, right? Unfortunately, the drinking water company in Galway did not know that, or pretended not to know this, right? So those things are important to keep in mind. If you want to solve a problem, you need to understand it. A crucial distinction that I'm going to talk about is the difference between flow pollution and stock pollution. And flow pollution is something that as soon as the economic activity ends, the problem is gone. And the classic example is noise. If your neighbor gets up at 6 in the morning to drive to work, starts his car, makes a lot of noise, wakes you up, right? Bloody annoying. But as soon as he left the street, the noise is gone, right? And the pollution is gone. Your annoyance may still be there, and your lack of sleep may still be there, but the noise pollution is gone. Stock pollution is the exact opposite. Nuclear waste is the classic example there. If we end nuclear power today, we will continue to have nuclear waste for at least another 10,000 years. Right? Because that is how long it will take to break down all the nuclear material that we have generated in our nuclear power plants. That is a stock pollution. The problem stays with us long after the cause of the problem has disappeared, right? And unfortunately for you guys, this matters a great deal in the economic analysis. So, what sort of target would we want to set? We're going to start, go ahead. Well, actually, most things are mixed, right? So the noise, I actually gave you an example, right? So the noise itself is acute, right? But the health problems that come from repeated exposure to acute noise can be chronic, right? Nuclear waste is a stock problem, but the risk of a nuclear accident is acute, right? So also nuclear power has sort of this mixture of stock and flow issues. And actually, whatever example you're going to look at, you always find a little bit of both, right? It's just that analytically we pretend that they're strictly separate. Okay, so we want to set the optimal or the efficient level of flow pollution. I'm going to call the damages of pollution D, pollution I'm going to call M for emissions, and I'm going to introduce the benefits of polluting activity and I will call them B. And there have to be benefits of a polluting activity, right? Otherwise we would never do that. If there's no some sort of benefit somewhere, then why would we pollute, right? The net benefits of the polluting activity is the benefits minus the costs. And if you want to find the efficient level of pollution, what we do is we want to maximize the net benefit. An unconstrained optimization, so we take the first partial derivative and we set it equal to 0. So the first partial derivative of the net benefit, delta and B, over delta M, right? That is the thing that we choose, is dB dm minus dd dm is equal to 0, or the marginal benefits equal the marginal cost. It's as simple as this. Let's do it graphically as well. On the horizontal axis, we have our emissions. On the vertical axis, we have some measure of gain, and in the brown curve, you're looking at the total private gains from emissions, right? And we emit very little, there's very little gains, that increases and increases and increases, and at some point it has to come down, right? And one example is heating your house, right? Yes, that generates sulfur emissions. And yes, that generates particulate emissions, and yes, it generates CO2. And those are all bad things, but it also creates warmth, right? And that is why you're heating your house. You're not heat your house to emit CO2. No, you heat your house to keep it warm. This is no heating, bloody cold. And then it gets warmer and warmer and warmer in your place. You emit more and more and more and more. You also pay more and more and more in your energy bill. That is something that you don't like. And at a certain point, it's warm enough, right? And different people put warm enough at different places, right? Some people are perfectly happy with a house that is 14 degrees. Other people say it needs to be 24 degrees. But at one point, you're paying too much, or it's simply too warm to be comfortable in your house, right? And you stop heating more, right? We all heat our house to a finite amount. And at that point, the private gains are actually beginning to fall. That is, it would cost you more and it would become more uncomfortable in your place if you were to heat it even warmer, right? That is why the brown curve has to come down. That's the total. Then the marginal looks like the dotted curve that you see here. And where the dotted curves hit 0 at Q prime, that is your private optimum, right? Now, this completely disregards the emissions and the costs of the emissions. And let's assume that that is given in the green curve. These are the social losses from these emissions, right? And we assume that right from the start, these are negative. So the brown curve is the private gains from emissions, and then the green curve is the damage that is done to the environment, right? And then what you need to do is you add up the two, and you come up with the red curve. It goes up first and then comes down at an earlier place than the brown curve does, and comes down faster than the brown curve does. And there's two ways of looking at this. Either you can say, well, the optimum is where the red curve goes flat, right? And that is where its optimum lies. Or you can say where the marginal social losses, the first partial derivative of the green curve, equals minus the first partial derivative of the brown curve, right? Those two expressions are mathematically equivalent. And that is the optimum that we want to strive for, right? So I first did it in calculus, and then I did it graphically. So this level here, for some reason there is no Q star, is our optimal level of flow pollution, right? And we can put a little bit more structure on this. And I'm going to talk about the areas A, B, C, and D. Here we have the Q star. This is the optimal level of pollution, the optimal level of emissions. This is the unregulated amount of emissions, right? So, what do these areas tell us? The area B, the integral under the marginal environmental damage curve, is the optimal level of environmental damage. Now, if I were to say this to an audience of environmentalists, or non-economists for that matter, there would be uproar, right? Because obviously the optimal level of pollution is 0. No. The optimal level of pollution would be 0 if there were no benefits from the polluting activity. Going back to the example of heating your house, the optimal level, or a 0 level of pollution, would be that either the outside temperature equals, or the inside temperature, indoors temperature, equals the outdoors temperature, right? And that is a 0 level of CO2 emissions for your house, right? Cannot be optimal, right? Because there's obvious benefits to heating a place, right? The area A plus B is the optimal level of the net private benefits to the polluter, right? That's the integral under the marginal cost curve, or the marginal gains curve, depending on from what direction you look at it. Again, this is greater than 0. And actually, as you can see, A plus B is greater than B, right? Again, that's one way of annoying environmentalists to say this. The area A between the two curves is then the optimal level of the net social benefits, right? Where the area under the green curve, A plus B, is the private benefit. The area B is the social loss, and then the difference between the two is A. That is how much society is better off by choosing point Q star relative to 0, right? The area C plus D is the amount of environmental pollution that should be regulated away, right? And the area C under the brown curve, under the private benefits curve, that is the amount of benefit that the polluter got at the expense of society. So that is the unwarranted level of pollution. That should be regulated away. Right? Optimal pollution is greater than 0. I'm going to talk a little bit more about this because, as I said, this annoys environmentalists no end that this is the case. And the reason for this is very simple. That essentially the laws of thermodynamics imply that 0 pollution implies 0 activity. And anything we do does some harm to the environment. Now, there is an exception to this, and that is that if there's a simulative capacity, that if you put a little bit of sulfur in the atmosphere, then nature gonna absorb it without doing any harm, then that's fine. We call that a simulative capacity. There's a bit of pollution that can happen without doing any damage. Surely that must imply that we then drive emissions to that particular level. Well, no, right? So the dark green was the original damage curve. Now I introduce a simulative capacity. Our first emissions do no harm. So rather than going through the origin, we go through 0 at a point further to the right. If everything else stays the same, then the green curve has shifted downwards. And that means that the optimum has not shifted here, but the optimum has actually shifted rightwards, right? In case of a simulative capacity, if the first bit of emissions do no harm, you actually can afford to emit more, and you can enjoy more of the polluting activity, right? You want to rile up environmentalists, try this on them. So, optimal pollution is greater than 0. It's also greater than the assimilative capacity. And that is because there's benefits to the polluting activity. So, that is for flow pollutants, noise, where things are simple. Now, unfortunately for you guys, we need to look at stock pollution, where the damage to the environment accumulates, right? So the damages of pollution are still D, but now D is a function of A rather than of M. The benefits of the polluting activity are still benefits of M, right? So nothing has changed there. But now we have this awkward A in there, and A follows this equation that you see here, that the stock of pollutants A at time t equals the stock of pollutants at time t minus 1 times 1 minus delta, where delta is natural degradation of our stock of pollutants. we stick nuclear waste somewhere. It has a half-life of 10,000 years. And that means that, yes, next year there will be a little bit less nuclear waste. In 10,000 years, there will be half the amount of nuclear waste, but that means that next year there will be a little bit less, right? And that little bit less, that is the 1 minus delta that you see there. So that is what the stock of pollutants would do. But then, of course, every year we add more to the problem, right? So part of the stock disappears over time, but we also keep adding more because that is what we like. The current benefits are still the benefits minus the damages, so nothing has changed there. But now, because it's a stock pollutant, we have a dynamic problem. So we should no longer maximize the net benefits or the current benefits, but we should maximize the net present value of this thing. That is, we take the benefits of our activity minus the costs of our activity at time t. We discount that back to today by dividing by 1 plus rho to the power t, where rho is the interest rate or the discount rate. And then we do that for all time periods. That is what the big sigma means. We add it up over all years. And that is what we call the net present value of our net benefit. And that is the thing that we want to maximize. Now, we have a problem. It's still an unconstrained, assume it's an unconstrained optimization. So we want to set the first partial derivative of this thing to 0 at every point in time, right? We're not making one decision, what should m be? No, we're making a decision, what should m0 be, and what should m1 be, and what should m2 be, all the way up to forever. So the first partial derivative of this thing to mt, actually nothing has changed, right? So dB dm 1 plus rho to the power t. This thing used not to be there, but now it is, right? It gets a little bit more awkward here because, well, the dm doesn't exist, right? Because it doesn't depend on m, but by the chain rule, because a depends on m, what we have is the d, the a, the m, right? But our a depends on at, depends on mt minus 1 directly, and then indirectly on mt minus 2, mt minus 3, mt minus 4. In other words, our emissions do damage this year, the year after that, and so on and so forth. So we need to sum into the future, starting today, or at time t rather, how damages at some point in the future, in some point after our emissions, how damages are affected then, and how the stock of pollutants is affected by the emissions at time t. And this, of course, happens in the future after time t, so we should discount this harder with t plus s, right? Boy, this is awkward, right? Now, you can't necessarily solve this. That's what I'm doing. But we can make it a little bit simpler if we assume that m doesn't change over time, that we are in the steady state. No, 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 no. I'm going to make an assumption later. I'm not going to make an assumption earlier. This derivative is actually simple. Because if we emit 1 today, we're going to add to the stock 1. And then next year, there's 1 minus delta left of that. And then in 2 years, it's 1 minus delta squared that is left of that. And in 3 years, 1 minus delta to the power 3 is left of that, right? So this term is actually simple. It's 1 plus delta s, right? So that's a relief, right? So we have 1 plus delta to the power s times 1 plus rho to the power s. Delta is how much the problem disappears over time. Rho is how much we care less about things that happen in the future. And that expression there is roughly equal to the expression that you see there. 1 plus delta s times 1 plus rho s is roughly equal to 1 plus delta plus rho to the power s, provided that your delta and rho are relatively small. Then I'm going to make an assumption of the steady state. I'm going to assume that things don't change over time. And the thing that doesn't change over time is the A, the stock of pollutants. And a steady state simply means that AT is always equal to A. So I can drop the subscript. That's a headache gone. If that is true, then that implies this, right? So we had previously that AT is AT minus 1 plus MT minus 1, but I could drop the subscripts because nothing changes. So we have A is 1 minus delta A plus M, or A is equal to M over delta. So that helps, right? So what we have is, well, because we're in a steady state, the marginal damage to the stock of pollutants is also unchanged, right? Because everything stays the same. So the D, the A, T, A sub T plus S, the subscript disappears there as well. And that simply becomes the DDA. Does not depend on T anymore. So we can bring it in front of the equation. Yay! And we are just left with this bloody thing here. Now, you know from your calculus that, and my daughter tells me that this is actually GCSE higher maths, that this series here solves as this one here. So now we're rid of those awkward summation sign. This term here can be simplified as this thing here. And we had that A is M over delta. And we can substitute that in here. And what we have is that the marginal benefits of pollution activity, the B, the M, equals the marginal costs of pollution, the D, the M, times delta times 1 plus delta plus rho over delta plus rho. And essentially what we have is the same thing as we used to have. Marginal costs equal marginal benefits, but because the benefits of reducing pollution, the marginal cost of reducing pollution equals the marginal benefits of reducing pollution, or the marginal benefits of creating pollution should equal the marginal damages of that pollution. That is still the same, but because the pollution is now sort of lingers in the atmosphere, or lingers in the soil, or lingers in the water, we're no longer interested in the marginal damages to the environment here and now, but rather we have a stream of those benefits. And because of that, we need to multiply that damage to the environment in the initial period by this term delta 1 plus delta plus rho over delta plus rho. We essentially need to inflate our damage to the environment because it's not just this year, but it is forever. That is why we need to multiply it. And that factor by which we need to multiply it depends on two things. One is the delta. How much does the polluting activity dissipate? How quickly does it disappear? And essentially, we go back to our stock pollutant. If we're talking about noise, then delta is 1, right? It's here today, it's gone tomorrow, right? It just all dissipates. So if our delta is large, the inflation term is small. And the other thing that matters is the rho. That is, how hard do we discount the future, which is essentially a measure of how much we care about the future. And we're going to talk, no, we're not going to talk about it. We're going to talk about it extensively next term if you're still with me, but not so much this term. How much do we lose interest in the future? How quickly do we lose interest in the future? That is this term here. And if both of these are large, then a stock pollutant essentially becomes a flow pollutant. And if both of these are small, then yeah, we're actually multiplying by a large number, right? And those of you who've paid attention to your finance, essentially we're treating pollution here because of the state assumption as a perpetual annuity, right? So much for cost-benefit analysis, or optimal pollution. Are there alternatives to doing this? Yes, there are. Otherwise, I would not start this way. I make this assumption that we can just compare costs and benefits, right? That the private gains from emissions, the brown curve, and the green curve, the social losses from emissions, could be set equal to each other. Now, you can only set things equal to one another if they're in the same unit. So if the marginal private gains are measured in utils, then I also assumed that the marginal damages to the environment are measured in utils, right? I did not say that explicitly, but as soon as you equate something, you equate something in the same unit. I cannot say that you are as high as you are heavy, right? That doesn't make any sense. I can say you guys are equally tall. I can say you guys are equally heavy. I cannot say you are as tall as he is heavy, right? That doesn't make any sense whatsoever. So I assume that everything was measured in the same currency. We're going to talk about that for the next 3 weeks. That is the big problem with cost-benefit analysis like this, and the main objection that a lot of people have. So there's all sorts of alternatives. One is multi-criteria analysis, which I think is a bit of a cop-out. In multi-criteria analysis, you say, well, we care about multiple things, and they called criteria, and we're going to look at them all together. I'm going to talk a little bit more about that next week. But the first thing you do in multi-criteria analysis is exclude all those policy options, all those scenarios that are worse than some other scenario on everything you care about. So a project that costs more is worse for the environment and increases inequality more than another project that should be excluded, right? And a multi-criteria analysis will tell you, yeah, it scores badly on all three things that I care about, therefore we should not do this. That goes without saying. As soon as you have excluded those so-called dominated options, you're back to cost-benefit analysis, because somehow you need to make those trade-offs anyway, right? So I think multi-criteria analysis is a bit of a cop-out. There's a lot of people who will be very cross with me for saying that, but I think that's the way it is. Typically in environmental policy making, people don't do cost-benefit analysis, but follow one of the alternatives that you see listed here. Multi-criteria analysis is something that academics do much more than practitioners or people who actually make decisions. One popular alternative is to set safe minimum standards. And this is particularly popular in things that relate to health. And it sort of sounds fine, right? We're going to sort of make sure that we don't do too much damage. We're going to make sure that we're safe. And it sounds very appealing, but how do you decide what is safe and at what level is that safety set and by which criteria? And if you look at additives to food, for instance, the way we declare them to be safe, and you all agree, I think, that the food that you eat should not make you ill, right? I think there's almost universal agreement on that. How do we decide whether or not you can put a certain E number in your peanut butter or in your pesto, right? It's very simple. What we do is we take this new additive, let's call it E103, and we feed it to 1,000 rats, or maybe we feed it to 10,000 rats. And so let's take the 10,000 rats in a certain dose. And if fewer than 5 of those 10,000 rats die after eating E103, then we say this is safe after they ate 1 milligram of E103. And the assumption there is that rats are a good model for humans. They are, because the metabolism is basically similar. If something kills a rat, it will also kill you, and vice versa. So that's a reasonable assumption. It's not the one-on-one. Rats are not people, right? And people are not rats, and some are. But it's an assumption, right? And there are things that would kill us, but not rats, and vice versa. So is that really safety? Also, the idea that it's 5 in 10,000, that's the right limit, rather than 6 in 10,000 or 4 in 10,000. And of course, 1 milligram of E103 is quite a lot for a rat, which is about this big, and it's quite a bit less for you, who are about this big, right? So there's all these assumptions that go in there about what is safe and what is not safe. That actually make this, it sort of like sounds like, yeah, there's a science behind this. No, there's a lot of arbitrary assumptions in what is declared a safe minimum standard. The other problem, and that's perhaps a more pertinent problem, is that these safe minimum standards look at the problem from one side only. The only thing that matters is human health. Now, that is a safe or a good assumption to make if we're talking about health issues. What if E103 also prevents us from developing prostate cancer? Now, the girls in the room don't care, right? You don't have prostates. This safe minimum standard saying, well, it doesn't immediately kill you, and therefore it would kill you, and therefore perhaps you should not eat it. What if there is, well, actually it's a pretty bad example, right? Because yeah, it may be that E103 prevents you from prostate cancer, but if it kills you before you can die of prostate cancer, you're just as bad off, right? So, sorry about this example. Sort of this idea of approaching things saying, well, it should be safe, assumes that there are no benefits to doing so, right? And sometimes you want to accept a little bit of food poisoning, if it comes to food poisoning rather than killing you, right? If it actually benefits you in the long run. Or you can say, well, we're going to accept a little bit more food poisoning if we can drive down the price of food, right? Which is good for those people who can't afford to eat, right? So approaching something as saying we're going to set a safe minimum standard essentially says this is a one-sided problem. I only care about food poisoning and worse. I don't care about the benefits of using this particular preservative or additive in my food. The same is true for the precautionary principle. It's essentially the same. There's two precautionary principles depending on what side of the North Sea you're on. The one interpretation of the precautionary principle is that uncertainty is no excuse. We're not going to talk about that. Essentially, it's that version of the precautionary principle says you have to know that things are safe before you can do it. This is a very strange thing, very strange decision criteria, right? You have to know that your marriage will succeed before you take your vows. You cannot know, right? If you intend to be married for somebody for 50 or 60 or 70 years, they will change in that period. You don't know what's going to happen. Marriages fail, right? Under that decision criteria that you need to know with absolute certainty that your marriage vows will hold, means that you should never vow those things, right? It's an absolutely silly way of looking at making decisions. The other interpretation of the precautionary principle says that it's better to be safe than sorry. Which is again a one-sided thing of looking at one-sided way of looking at decision problems, right? That you should, and this is the prevailing interpretation in the European Union, that we should not introduce new pesticides into agriculture until we know that they won't do any environmental damage. And you may think, well, that's a good rule, right? We should not be doing things unless we know that they are safe, and we should not be introducing new chemicals into the environment. It makes perfect sense if you are talking about virgin agriculture that does not use any pesticides. Really, the rule that you want is that we should not be introducing new chemicals, new pesticides into agriculture that are worse for the environment than the ones that we're currently using. That would be a good rule, right? But saying we should not introduce new chemicals into agriculture, new pesticides into agriculture, essentially what you're saying is continue to use the old pesticides, guys, which may be much worse than the ones that are newly introduced, right? So again, it approaches things from one side only. It just looks at, could this intervention do any harm? If so, don't do it. The implication then is that you continue to do whatever you were doing before, which may be worse, right? So that is also essentially a way of pretending that there's no trade-offs to be made, right? Another way of setting environmental standards is to use best available technology. That is, do the best you can to avoid environmental damage. Problem with that is if you ask an engineer to come up with a neat way of solving a problem, they will. That's what engineers love to do. And if you say, well, just come up with the best way of solving this, they're gonna completely over-design and make a fanciful contraption that is exceedingly expensive. And that's it, right? So you can't do that, right? Best available technology is not really an option. It's sort of like you're in NASA territory, right? Where they just spent, if you compare the cost of space flight from NASA, it's essentially has been on the charts to use the best available technology to the one of the commercial space companies. There's a factor 1,000 difference between the cost of a launch, right? That's what happens when you give engineers free rein and an unlimited budget. So typically, best available technology is sort of changed into best available technology not exceeding excessive cost. And then you're again back in cost-benefit territory. What cost is excessive, right? So that does not really help either. Another way of setting targets for environmental policy that is getting increasingly popular is to use citizen juries. And it used to be that people held referendums on this. Not in this country. We have a hesitance to use referendums for a good reason. And we've just been reminded just how awful referendums can play out. But in other countries, it's actually fairly common to hold referendums on environmental issues. And one example that comes to mind is a referendum that was held in Sweden, whether or not Sweden should have nuclear power. And that is one way of solving it. The problem with this particular referendum that was held was that actually in sort of like interviews that were held, surveys that were held after the vote, turned out that many of the people did not know really about nuclear power, why you would want to use it, whether it's advantages, whether it's disadvantages. They just voted for it because somebody had told them some nonsense about nuclear power. And there's two sorts of nonsense about nuclear power. Either that it's incredibly dangerous, and the other is that it will solve all the problems in the world, right? And depending on who you listen to, it's typically either of the two extremes, and the truth lies somewhere in the middle. So they later repeated this referendum as follows, that you first had to ask certain certain factual questions about nuclear power, and only those who got the answers right, only those votes counted, right? Is that democracy? But that's what they did. Now, citizens' juries are a variant on this. There's sort of the idea is that if you just ask Joe Sixpack on the street what they think of something, you get a pretty uninformed answer to what is typically a very complex problem. So citizen juries go around that. Essentially what you do is, instead of asking everybody in society, you take a representative sample of people, you put them in a room together, and if it's a simple problem, you put them in a room for an afternoon and then let them decide what should be done. And if it's a complicated problem, you stick them in a room for 6 weeks and then let them decide. And I'm not kidding you, France has been through an exercise like this, where indeed people had to dedicate 6 weeks of their lives in studying climate change and the solutions to climate change and the impacts of climate change before they came up with a recommendation of what France should do about its greenhouse gas emissions, right? The Netherlands has gone through a similar exercise. And then a representative sample of people, all walks of life, and then they sort of come up with a recommendation of what should be done. It's one way of solving problems. It sounds democratic. You solve the problem of ignorance, because during those 6 weeks they were not just sitting in the room. No, they were discussing amongst themselves. They were interrogating experts. They were listening to talks. They were reading material. Right? That's not in the room for 6 weeks. So that is a reasonable way of doing things. You could also say, well, why do we have parliament? Isn't that their job? Didn't we elect these people to make these decisions? And didn't we elect people who thought had a good knowledge and a good view about these things? So citizens, juries, doesn't that just like take away the role of parliament? But that's a completely different solution, a completely different story. So those are ways of setting targets. Most targets, by the way, are fairly arbitrary. Most targets that are set for environmental policy is essentially if it's big target for big things, it's essentially a power play among senior politicians. How the target is set for things that are sort of go under the political radar, it's a committee of civil servants who decides this and then gets it signed off by Parliament. Most targets are set on basis of reasons that are not entirely transparent or entirely reproducible. But that is the way of the world. Now, economists come back into the analysis. So economists prefer cost-benefit analysis, right? Economists come back into the analysis in so-called study of cost effectiveness. That is, after a target has been set, and it may be a completely arbitrary target, what is the cheapest way of meeting that target? So efficiency says we should set the target at the optimal level and then obviously meet that target at the lowest possible cost. Cost effectiveness said we should set a target at some level and then meet that target at the lowest possible cost, right? So efficiency applies cost effectiveness, but cost effectiveness does not apply efficiency, right? And in the pre-lectures about policy instruments, we're going to talk more extensively about cost effectiveness analysis and cost effectiveness and how to guarantee that. Okay, it is 14 minutes to 3. What I have left is the super sewer and how to do cost-benefit analysis in practice and everything that can go wrong. I suggest that you read that, perhaps watch the video of last year. Next week, I'm going to move into monetary valuation because I can't lose time on that.